So recently we have been looking at mean, median, mode, and range, and mean absolute deviation of a set of data, and those are great numerical ways to summarize data. But there are other ways to do it, and we can do that visually through graphs. So today we're going to start looking at graphs and how data is shown on a graph. Specifically today we're going to look at line plots, which are also called dot plots. These kind of graphs use either a dot or an X, and those are to show the individual pieces of data. Generally, you do them on a number line, though that doesn't necessarily always have to be the case. So looking at this particular graph, it's graphing the heights of 6th graders in first period math, and we're graphing it in inches. Now, it's important to know what each X stands for. On this particular graph, each X is going to represent one student. And it is possible for it to stand for more than one student, but only if we had a key that told us that was the case. For example, if it said X equals 2 students, then we would know that each X was for 2 students. But since we don't have that, we can go ahead and assume that each X represents one student. So I can tell things on this graph. For example, I can tell that there are 4 students that are 62 inches tall. 1, 2, 3, 4. I can tell things like there are 5 students who are shorter than 59 inches. 1, 2, 3, 4, 5. Those are all shorter than 59 inches. I can see things, for example, like that the shortest person is 57 inches tall. The tallest person is 66 inches tall, so forth and so on. Now, if I want to, I can also look at how we make a dot plot. So let's take a look at that real quick, and then we will compare some line plots or dot plots. So looking at this one, for example, we're going to notice that we want to make a dot plot of students who are in second period math. And if you've been given a list of how tall they all are, and looking at this list, you might think, oh, I should put them in order from least to greatest, and then I can go ahead and do that. That's not actually all that helpful. What is helpful is picking out your shortest and tallest people. So for example, 65 inches tall is the tallest, 55 inches tall is the shortest. So what that means is on my number line, I have to have values that are at least starting at 55 and going at least as high as 65. I could go lower and higher if I want, but that's not necessary. So I'm going to start with 55, 56, 57, so forth and so on. Now notice, as I'm doing this, that I'm trying to be pretty careful to evenly space my numbers on my number line. And the reason why I'm being pretty careful is because if I don't have them spaced evenly, that's going to change the appearance of my graph. And if I change how my data appears on the graph, people might make incorrect conclusions. So it is important to try to space evenly. Now again, you may think, well, the next thing I should do is find how many are 55s and then start mark that many X's, and then find how many are 56 inches tall and mark that. That's actually probably going to be harder. My suggestion is just start with the list and go in the order that it is and mark the X's as you go. So our first person is 65 inches tall. I'm going to mark an X at 65 inches and mark it off my list. Then I'm going to mark an X at 64 inches, mark it off my list. Put an X at 65 inches, mark it off my list. Put an X at 63 inches, mark it off my list. Put another X at 63 inches, mark it off my list. Put an X at 59 inches, mark it off my list, so forth and so on. Notice I am trying to make all my X's about the same size, and I'm going to try to stack them about the same spacing. So finish up your graph, and when you're done, take a look at yours to see if yours matches mine. All right, now that you've had a chance to do this, when you look at it, you should have one person that's 55 inches tall, one that's 56, two that are 57 inches, nobody was 58 inches tall, two that are 59 inches tall, so forth and so on. So now, if we wanted to, we could compare this class to our first period class. So when I look at those two graphs side by side and I want to compare which class is taller, I might look at that and say, well, I think that class 1 is taller because the tallest person is in class 1. That's 66 inches. Well, that's a true statement, but that's only one person. When I look at these two graphs, I'm going to notice that I have more students in class 2, second period, that are on the high end And on the other class, first period, I have more of my students sort of on the lower end of the heights. So that's going to tell me that I think probably class 2 could be described, or second period could be described as being the taller of the two classes. Now, again, let me point out to you, class 1 rather, first period, has 28 students, and I know that because there's 28 X's. Class 2, second period, has 27 students because there's 27 X's. That doesn't mean anything as far as which class is taller. It simply refers to the number of students in the class. All right, now let's look at another one. Take a look at this one, and looking at this dot plot, see if you can answer some questions about it. Students in one class were asked how many siblings they each have. The dot plot shows the results. So, looking at this, let's see if you can answer the questions that are given here. All right, now that you've had a chance to look at them, and if you're not done, make sure to pause before you go on. Now that you've had a chance to look at them, there's one student that has 6 siblings, right here. There are 3 students that have no siblings, right there. There were 11 students with 3 or more siblings, because I have to include anybody in this column, this column, this column, or this column. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. There are 20 students who were surveyed because there are 20 dots in all. Now, if I ask you these next couple questions to find the mean, median, or the mode, median, and range, mode is 3 because more people have 3 siblings than any other number. The median is also 3, and the reason the median is 3 is it's not because I say not 0 and not 6, not 1 and not 5, not 2 and not 4, it must be 3. That's not why. I have to look at this instead as a whole list of data. So my data are 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, 3, 3, 3, 4, 4, 4, 4, and then 6. I can look at this on my dot plot and kind of work my way toward the middle by saying, well, it's not these 3 students because they only have 0. And then I'm going to cross out 3 of my students who have lots of siblings. So I'm going to cross out that 1 student there, 2, 3 students. I'm not to the middle yet because I still have more than 1 student there, and more than 1 student who's represented. So I need to start crossing out more students. Cross out everybody that only has 1 sibling. That's not going to be the median, it doesn't look like. So now I need to cross out 3 students who have a higher number of siblings. So 1, 2, 3. Now I need to cross out, keep working my way toward the middle, and I'm going to cross out, maybe I want to cross out next 3 students that have 2 siblings. And then I can cross out 3 of my students that have 3 siblings. Notice what that leaves me in the middle here. I have 2 students there in the middle that each have 3 siblings. So what's the median? What's exactly between 3 and 3, of course? 3. So that's why 3 is my median. My range is 6, and I got that by doing 6 minus 0. For the mean of this one, it's really important to recognize how many times each number of siblings has to be represented. There were 3 students who have 0 siblings. There were 3 students who have 1 sibling. 3 students who each have 2 siblings. 6 students who have 3 siblings each. 4 students who each have 4 siblings. And 1 student who has 6 siblings. So when I look at that, I have to do those multiplications to figure out the total number of siblings of all the students in the class, and then divide by 20 because there were 20 students. So that gives me 49 divided by 20, which is 2 and 45 hundredths. Now, can you actually have 2 and 45 hundredths siblings? Of course not. But statistically speaking, that is the average or mean number of siblings that the students in this class have. Now let's talk just a little bit more about now that we've looked at line plots, let's talk a little bit more about what data can look like on a graph. We can talk about that in terms of peaks. That's a piece of data that occurs the most often. It's going to be your highest. Think about a mountain peak. It's going to be the highest point on the graph usually. A cluster is a place where the data is grouped together closely, and a gap is where there are no pieces of data. So, for example, looking at some line plots, these are line plots that reflect the scores of 4 classes on their calendar tests. So they're very different. but I can identify some peaks, gaps, clusters, things like that. For example, in first period, they peaked at an F. Not so good. In second period, the peak was a B. That's better. In third period, the peak is a C. And in fourth period, the peak was at an A. So all of those have a peak. That's basically where your highest point is. And that's also going to be your mode. So the mode for first period was an F. The mode for second period was a B, so forth and so on. When we look at gaps, none of these show a gap except for fourth period. There's a big gap here. One student made an F. Everybody else made A's and B's. So there was a big gap between that one student and the rest of the students. There are some places on the other graphs where there might not be a lot of data, but there's no other places where there's no data. And then clusters. When I look for a cluster, probably the best example of that is in fourth period right here where I have a lot of data together. That's going to be a cluster because that's where a lot of my data is grouped really closely together. Now you might call some of these others clusters. For example, you might say second period is mostly clustered between A, B, and C. You could maybe say that, but probably fourth period, that's your best example of a cluster. We can also talk about some of the just general shapes of a graph. When you look at this, when you look at these graphs, the graph for third period has what we call basically a bell curve. Because it's the data, if we drew a line above it that sort of mirrors the shape of it, it's going to more or less look like a bell. And that is also called symmetrical data. It's more or less symmetrical, meaning if we could fold our paper in the middle, if we could fold our screen in the middle, the two sides would more or less fold on top of each other. So that's pretty symmetrical data. Some other ways we can describe data. We can describe this data, for example, for fourth period as skewed left. It's skewed left because most of our data is on the right-hand side, but we have a tail, a little bit of data, that's on the left. And we could probably describe second period that way as well. It's more skewed to the right, skewed left rather, because we have sort of some data that's over here to the left, but the majority of it is closer toward the right side. But fourth period is definitely our best example of skewed data. All right, let's look at one more example. Here's an example of a different kind of graph, which is a histogram, which we're going to do in another lesson. But I want to point out to you, we have a definite gap right here in the data. We have a peak here. We have a cluster here. And we could more or less describe the shape of this data as being skewed right. It's skewed right because the majority of our data is on the left-hand side, and there's this tail-looking thing where there's a little bit of data here on the right-hand side. So this one is called skewed right. This is a graph that is skewed right. Hopefully this has given you an idea of graphs and sort of what the shapes are, what they look like, and how to describe them.